In this video, I will show how to solve a system of ordinary differential equations in R. R is a free software tool that you can download from the following website. After you have installed R, I recommend that you also install RStudio, which extends the basic R version with a lot more tools. Once you open RStudio, it will look something like this. We should first open a new script in RStudio. We then enter the code in this script. We will here start to solve the following simple differential equation, which might represent how the amount of caffeine in the body is changing over time after a cup of coffee. The initial value is here 70, which means that the amount of caffeine is 70 milligrams at time point 0. The caffeine molecules are here assumed to be eliminated from the body at the rate of 0.2 per hour, which means that approximately 20% of the caffeine molecules are removed from the body every hour. The following code can be used to solve differential equations in R. Note that you can set up the code in many different ways, and that this way is based on my personal opinion to create a simple code. We will here go through this code step by step. If you have not installed the package deSolve, you first need to run the following line in R to install it. After you have installed the package, you need to load the package. Before I run the code to solve the equations, I usually clear the memory because it might be tricky to find an error in the code if old objects are confused with new ones. The deSolve package includes the function ODE, which can be used to solve the ordinary differential equations. The first argument in this function is the initial state values, which are the initial values of the variables. The initial value in our example is 70. After we have assigned the initial values to the variables, we create the vector of the initial values. That vector is the one we place here. The next argument in the ODE function is a time vector. In this example, we use a time vector with the sequence of numbers that starts at 0 and increase with the step size of 1 up to 30, like this. The step size only determines what step size you will see in the output. It does not control the step size of the actual solver. The third argument should include the name of our function where R can find the ordinary differential equations. This is the function that we will use to define our equations. Note that these two must have the same names. This function receives the time vector that we previously defined, and the initial values. To be able to use the name of our variable n in the equation like this, we can use the function with, so that we can access the names of the variables in the state vector within the function. If we do not use the function with, we have to extract the variables from the state vector like this, which is more complicated to work with. We also need to create the vector where we save the output in. Then we simply define our equation and return the calculations to the ODE function. The name of this object is dndt, but any other name works as long as it is the same name at these three places. The last argument in the ODE function is where we should place our parameters. However, I usually do not use this argument, which is the reason it is here set as null. Instead, I define the parameters as global parameters, which means that they are directly accessible in the function. We then run the code. The output from the ODE function will be stored in the object that I have here called out. We then use the function plot to plot the output as lines, which results in the following plot. We'll now see how we can change the code to include several equations. Once you get the idea of how to set up the code with 2 equations, it is easy to extend the code with more equations. We will here solve these 2 equations with the following initial conditions and parameter values. We simply add the second equation like this. Since we solved 2 equations, we must also add the initial value of the second equation, which is here set to 0. We also need to add this initial value to the vector. Note that it is super important that the order of the initial values is the same order as the corresponding equations. The first equation describes the rate of change of the variable n, which means that n should be at the first position of the vector, whereas b should be in the second position, because the second equation represents the rate of change of b. Since we have a new parameter in our equation, we need to define that here. If we now run the code and print the first 6 lines of the output with the function head, we see that the first column includes the time points with a step size of 1. The second column includes the values for variable n, whereas the third column includes the values of variable b. To plot how the variable n changes over time, we therefore plot the values of the first column against the values in the second column. And if we like to add a red curve to this plot, where we draw how the variable b changes over time, we can use the function lines to plot the first column versus the third column. This will generate the following plot. To denote which curve that belongs to which variable, we can use the function legend, which will put a legend up here. Note that there are a range of different solvers to choose between by using the argument method. Okay, so once you have entered the code like this, it should be easy to just run the code, and we can see the output in this plot here. So now we can change a few things. For example, suppose that we start, instead of 70, we start from 200. So I changed the initial condition to 200 instead. And I can run the code, and I don't need to run this function again because it's already stored in the memory. So now it starts at 200 instead. And we can also change the time, because we simulate 30 hours here, but we can go, for example, to 60 hours. And now you can see it goes almost down to 0 here. And if you print the output, we can see that these are the time points, and these are the values for the first and second variable. So the first equation and second equation, which are the ones that you see here and here. So if we change this to, for example, 0.1, and we run this code and check the output, you see that the time points now go from 0 to 0.5, because the step size in the output is 0.1. And note that this is just prints the first 6 rows. So if you print the full output here, I have all rows here, which are exactly the ones as used for this plot here. This was the end of this lecture about solving ordinary differential equations in R. Thanks for watching.